I don't know exactly how that happens. It defines logic.
No,
So that was end of last week. Got the first prototype of my Ola Gabby.
So I would recommend
Pretty
seeing
well.
him.
Yeah.
Yeah. I specifically like the fact that he spoke in Spanish and responded with English context.
Yeah, right. You know, it really shows that we're not just echoing back what we heard.
Exactly.
Yeah.
But
But it's also
that bottom layer with the
it's just that much easier for us to do as well. Because all we have to have we just changed the network. That's all we need. Hola, Gabi. Ore, obrigado. Hola, Gabi. Ore, obrigado. That's multilingual.
yeah. Oh, really? I should mention the relation now.
Okay.
Feel free to unmute, but you might hear. So let it.
Hola, Gabi. Hola, Gabi. Mando once. Hola, Gabi. Mando once. Hola, Gabi. Mando 10. Hola, Gabi. Mando 9. Hola, Gabi. Mando 7. Hola, Gabi. Mando 10. Hola, Gabi. Mando 6. Hola, Gabi. Mando 6. Hola, Gabi. Mando 6. Hola, Gabi. Mando 3. Hola, Gabi. Mando 3. Hola, Gabi. Mando 3. Yeah. We're always finding things. But yeah.
Oh, it felt like you put one in for Spanish.
I have two different. I have two
Oh, that's funny.
harvesting.
Little energy harvest.
That could do better.
Okay, So it's already streaming. Yeah, we need to get the presentations. Here you go. Thank you. I hope so. I want to spill my water on that. Oh, that's a microphone. Yep, we're live streaming right now. YouTube. That's we try to do that. That's the whole. All the slides are available. Hold on one second. Okay, okay.
yours. Ping you.
Coming over the slide. I'll hire you right now. I guarantee you. I don't have to do the carpet dropping thing. I know.
They actually have working motors.
Are you serious?
It is a perfectly timed. Perfectly timed. No, races with the
And if you
So
supposed to be the public.
I officially there's something
Good evening, everyone. Thank you for coming to the tinyML meetup. This is the last meetup we have for 2019. We've had a very successful series of meetups this year, and we have to thank you all as a community for showing up in full strength and making this a grand success. And we hope to have many more in 2020 as well. So we have some links up here. QR codes for joining our meetup group and our LinkedIn group. If you want to keep getting notifications about upcoming events. I'd like to make a couple of announcements. I forgot to get the clicker. I'll look at that. Thank you. Perfect. First of all, I'd like to thank ARM, our sponsors, for both providing this wonderful venue and refreshments. I think the tinyML meetup folks got fed more than the ARM event folks, so that's really awesome. Thank you, Wei, for that. I'd like to make another announcement, just kind of a reminder that we like to do. The tinyML second annual tinyML summit is happening in February in San Jose, and please go to tinymlsummit.com to sign up if you already haven't. We've got an amazing lineup of talks. We have a day 0 workshops session. We have multiple workshops planned, so we look forward to seeing all of you there. So with that, I'd actually like to turn this over to Wei Xiao from ARM, and she's going to introduce our speakers. Thank you.
Thank you for joining us today. If you had the chance to join us in the Meetup Dec Summit early today, we hope you had a lot of fun. So our first talk today is neural network optimization for on-device AI. Our speakers are Elsie and Naveen from a forward-looking research team within ARM. They will share some of the techniques for model optimization. I'm going to hand over to Elsie.
All right, thank you. And good evening, everyone. Thank you for coming in despite, the very difficult traffic and almost impossible weather. So again, thank you for being here. Hopefully, for the next 30 minutes, our content, especially the sharing of experiences and knowledge we have developed on neural network optimization for on-device AI can be very helpful to the audience. So the speakers will be myself, Elsie, and also Naveen. So for this particular audience, I guess, this first slide is very easy, right? Why is machine learning moving to the edge, right? So simply put, we cannot defy the laws of physics and economics because it takes tremendous amount of power and bandwidth to move the data from billions of devices to the cloud and then get the results back. And also in this process, it adds up to the cost and also the latency and reduce the user experience, not to mention the pressure on making sure every single component in the system are done reliably and also securely. But when we talk about edge applications, different people have different perspective. What it means by edge. Actually, we're looking at a very wide range of application, starting from the bottom left, your smart speaker that has some simple keyword detection capability, all the way to the autonomous driving cars. and everything that happened in between. And then for the audience today, we can say that the region that covers the tinyML is typically devices that are smaller than the smartphones. So it's very difficult to enable on-device machine learning, and we're facing a tremendous amount of challenges. The first level of challenge is about enabling the deployment, because the tiny edge devices tend to have highly constrained resources for deploying sophisticated and complex machine learning algorithms. For example, the devices tend to have very limited memory, and also they have very limited compute capability. And these devices are usually powered by M-class processors from ARM. And the same kind of a challenge continues when we move on to the mobile world. But then we also are challenged with a different level of complexity here, especially the hardware features. So the diagram on the right side shows the newly introduced family of NPUs introduced by ARM. They're called Ethos. And we have N37 all the way to N77 for small, medium, and large NPUs. And you can see that NPUs are very different from the traditional processors that include both M-class and A-class. So here we can see that these hardwares are defined and designed with very special hardware features, such as very efficient compression hardware for both activation and wait data, as well as, for example, for the core operations like Conf2D, the Ethos family of NPUs have developed something called a Winograd convolution, which really speed up the core of neural networks. And also the accelerators are optimized for integer arithmetic. So this kind of a diverse and complex hardware features are non-trivial for us to take advantage and really the full potential. Therefore, it is very important, in fact, it's our key vision in that on-device machine learning solutions would actually contain three major components, starting with model optimization, followed by a good system software and good hardware features in order to utilize all of the special hardware features, as well as to address the actual challenges for on-device deployments. So here we zoom in a little bit more into what we mean by the three major components. If you look at it from an end-to-end technology exploration perspective, the input of this system will be your typical machine learning models. They may take signal as inputs such as vision, voice, or vibration. And the outcome of that will be realistic and reliable performance, power, area, and bandwidth numbers. So we have mentioned that there are specially designed hardware features as well as very challenging constraints for us to address. And the only way to enable that and fully explore from end to end is to add this new module called model optimizations, which is the focus of our talk. And this, all the three major components combined, is something that is required to enable the code development in the algorithms, the software, as well as the hardware. So now we take a further look at the landscape of model optimizations, right? So you can see that we have this general plot that explains the different scenarios when it comes to the accuracy and the performance. So along the x-axis, we have a generic term called optimization strength. And then along the y-axis, we have a normalized accuracy. And this whole landscape can be roughly divided into three sections. The first region is something that, when you have implemented the proper technique and also done things carefully, you can achieve minimal accuracy impact while introducing small to medium optimization. So there's almost nothing not to like about this first region. Of course, typically this region will require some access to the data. And the second region is where we're going to see the trade-off between the accuracy and performance. As we crank out the optimization strengths, you're going to see more noticeable degradation of the accuracy. So this is important to offer the options to be able to trade off between accuracy as well as the performance or the optimization stress. And the third region, which is the far right, is where we call the highest performance region. This is where on device you're highly constrained with resources, but you have to enable the deployment. So here the question is, in order to reduce the model size and introduce a bunch of optimizations, to satisfy the constraint, what is the best possible model that we can produce in order to achieve the best possible performance? So here again are the three typical scenarios when it comes to model optimization, and especially its trade-off between accuracies and the optimization stress. So here is a quick overview of the model optimization workflow. It has three major building blocks. The starting point of this process can be either trained or untrained models. And the first step is something we call algorithmic optimizations, okay, where we will do algorithmic transformations to change the computation workload of the network while maintaining roughly the same accuracy. And then the second step is something we call network optimizations. So here we're introducing different variants of pruning, whether it's structure pruning or magnitude pruning, as well as weight clustering. In this process, we have probably by now all identified the importance of defining and optimizing for the so-called hyperparameters. Here, every optimization requires its own set of hyperparameters. So we have investigated different ways of optimizing and deciding for those hyperparameters, which we're going to see some examples later. Here, the typical ways are some of the well-tested heuristic, or something that is based on reinforcement learning, or the more classic optimization methods such as simulated annealing. And when you have reinforcement learning in the loop for the model optimization, the process may generate some intermediate models we actually use as a way to train your reinforcement learning agent in order to make better decisions to decide on those hyperparameters. So after the network optimization step, we'll have a partially optimized model that are ready for the next step, called a deployment optimization, where we introduce a lot of interesting optimizations, such as equalization, the folding of batch norm, layer fusion, and quantization. So every individual optimization in this picture, if you search, you're going to see tons of publications. So by itself, it's already introduced a lot of complexity. But recall that our goal is about introducing end-to-end exploration. So I want to point another dimension of complexity in this model optimization scenario, something we call collaborative optimizations. In that, if you're doing a sequence of optimizations, the later optimizations need to be aware of what has happened before that, and needs to have a way to properly preserve the attributes introduced from early on, right? For example, if you do pruning first and then you do clustering and then quantization, then you better be sure that a cluster optimization that you do can properly preserve the sparsity, right? Similarly, if you end a process with quantization, then the quantization needs to be able to preserve all the attributes introduced from earlier optimizations, right? So this is similar to the idea that one model will verify all the hardware features that we want to explore. So here are some of the numbers, and so we have investigated across a wide range of application domains, from image classification to object detection, speech recognition, and so on. So here are just some of the examples, and they're mostly just models for image classification. For example, for Inception V3, we can prune the model to be 50% sparse and cluster every single layer to just 5-bit indices, meaning that every layer has just 32 centroids. And also we have fully quantized the whole network from FP32 to just 8-bit. And also a note here about quantization, it is done via post-training quantization. So if we enable fine-tuning in the quantization process, this accuracy will further recover, okay? But even without that, we see that when we combine all the aggressive optimizations, the accuracy degradation is just 1%, okay? And similarly for ResNet 50, with the same level of collaborative optimization, we have seen similar accuracy degradation. And then the interesting case is VGG 16. We've done the same level of sparsity pruning as well as quantization, and we actually try to be very aggressive for the clustering. Especially, for the last 3 big layers in VGG, we have successfully clustered those layers to each using only 3 clusters. When we combine all of them, we see a slight increase in the accuracy. So this is the power of model optimization, and also the importance that you have to properly combine everything in a collaborative fashion so that your final model can be used for end-to-end exploration of technology. And of course, all the combinations or optimization wouldn't matter if they don't introduce something otherwise would not have. So in this case, the optimized models have reduced the model size, and also it has drastically increased the compressibility. Using exception V3 here as an example, with combined optimizations, we can compress the model by an order of magnitude. So that really reduce the size of the model, making it possible for deployment on highly constrained edge devices. And of course, these kind of optimization would also enable efficient on-device computation. So again, I think this is just to echo back to our key vision that a complete on-device ML solution needs to have model optimization in the loop. So recall that there are 3 main steps, the first one being algorithmic optimization. So let's take a couple of examples to see what we mean by algorithmic optimizations. So here on the left side is something we call complex domain vinaigrette. This is a pretty mathematical concept, and this is an innovation done here at ARM in that we have taken the counterintuitive way in the derivation of the complex vinaigrette. We have actually taken the plus minus I of the complex root of unity as interpolation points. And in return, we have derived a set of the so-called complex domain vinaigrette. And they have very amazing advantages compared to the best known traditional vinaigrette algorithms. So here we are comparing against a very popular and heavily optimized library called NCNN, developed by Tencent. And we are comparing against their fully vectorized integer kernels for 2x2 and 4x4 vinaigrette. And you see the blue bar on top is the ARM special version of the complex 4x4 vinaigrette. And we can see that on the kernel level, our kernel is in fact the fastest integer vinaigrette kernel in the world right now. And it achieves more than 2x performance of the baseline, which is the fully vectorized 2x2 vinaigrette. And then when you move on from the kernel level to the network level, depending on the percentage of your optimizable conv2ds in the network, for VGG 16, it really, just make it go way faster. We're looking at roughly 95% of the speed up for the entire network of VGG 16. And as you have a less and less percentage of optimized conv2d, you can also see this speed up decreases. But again, this is a purely algorithmic, meaning that as long as you have optimizable conv2ds in your model, you can benefit from this new algorithm invention. And the side effect of applying vinaigrette is that it will start the algorithm with something called a pre-transform. So if you have like an incoming 8-bit models, as soon as you apply some simple matrices for a forward transform, you're gonna have to extend the intermediate result to 16 bits. So on the right side, we're further pushing the envelope there to see if it is possible to constrain the transformed data to also within 8 bits. So if we can enable this, we can essentially double the SIMD vectorization, right? Pushing that at 2x to somewhere above 3x for the vinaigrette kernels. So here we're showing some early results, and the more interesting results are on the bottom right side of the table, where we're comparing the inception V3 by replacing the regular conv2d with either real or traditional 4x4 vinaigrette, or with an ARM-specific complex 4x4 vinaigrette. And we can see that without training, the traditional 4x4 kernel basically has lost all the accuracy, right? So So these numbers are not the accuracy delta, they're the actual accuracy. So you can see that without retraining, the conventional or traditional real 4x4 simply does not work. But then with retraining, although it is able to recover a lot of accuracy, but there is still a large and unacceptable gap from the baseline. On the other hand, if you simply drop in, replace the real 4x4 with a complex 4x4 kernel, you can see that even without retraining, we only see about 2% degradation for top 1 and 1% for top 5 accuracy. And then with retraining, they recover the accuracy really well, while giving all the speed up that we've seen from the left side of the slide. So here are just a couple examples for what we call the algorithmic optimization. Next, we're going to move on to the network optimizations and also the deployment optimizations. The first one we're going to cover here on the network optimization is pruning, right? So we like sparse models, right? They compress better, and if you have special kernels or a special hardware, they can really exploit the sparsity in your model parameter. So here are the 3 typical flavors of pruning. The first one is a magnitude pruning, where we turn up some of the small values to 0 in order to improve the sparsity. The middle one is channel pruning, where we can selectively prune away the whole channel. And then also, as a consequence, when you remove some of the channels of the current layer, some of the kernel that were used to generate these channels can also be pruned away, right? And the rightmost is something we call structure pruning, or more specifically, the strided or a block pruning, meaning that as we improve the sparsity, we're going to introduce some sort of a structure, whether it's a stride between the non-zero values or some sort of a block structure in the pruned network. So you can imagine that if your CPU has a SIMD, gather, and scatter instructions, then they can be used to accelerate the execution of this kind of structured sparsity in your pruned network. So we're also going to use pruning as an opportunity to talk about a hyperparameter optimization, because it's really important, and it's also part of the reason why people call deep learning alchemy, because those hyperparameters really just either make things work or break, right? So on the left side, talking about the pruning in particular, we have 2 ways, in general, 2 ways of optimizing for those hyperparameters, namely the deterministic and the reinforcement learning based. A third one is called a simulated annealing, which is not shown here, but we also have investigated at R. So for the deterministic, the most straightforward way would be like if we say we want to introduce 80% sparsity into our model, and you have multiple layers that you can prune. The most straightforward way is that, okay, I'm going to prune every layer to be 80% sparse. But we know that different layers in the model would have a different sensitivity and also different importance when it comes to the impact towards the final accuracy. So we have investigated in this heuristic where we'll introduce per layer target sparsity based on the number of parameters of that layer. And also when we combine all the per layer sparsity together, it will still satisfy the overall sparsity for the entire network. And this, you can see that it is inspired by the publication from the research community. And also, every time we prune the network, it's equivalent. You can think of it as introducing some damage to the network, which means it will need some time to recover from that damage. So it is also important to dynamically increase the pruning ratio during this optimization process. So you prune and introduce some damage, and then you recover, and then you prune again with a higher sparsity target. So you gradually turn up your target sparsity. So what it means is this is a typical pruning process once everything is done correctly and carefully. What is shown right here is that we're tracking the top 1 and top 5 accuracies on the top row and the sparsities on the second row, right? You can see that throughout this entire process, we have successfully maintained both top 1 and top 5 accuracy. On the other hand, we have successfully increased the sparsity of the model, in this case from 0% to 50%. Okay, so that is the importance of using well-tested heuristic or some form of reinforcement learning-based method to properly distribute your overall sparsity onto different layers and also properly schedule your target sparsity across the entire process of optimization. I also want to point out, some interesting detail right here. You see that the per layer target sparsity is associated with the logarithm of the number of parameters in that particular layer. Lately, we have developed both empirical and theoretical understanding and some insight. Essentially, recall that in the earlier slide, we need to have a curve that will trade off between the accuracy degradation and optimization strength. So here is an example for some models, just based on its definition, we can actually derive a nice curve that will show you the relationship between the sparsity and the accuracy degradation, right? So this would offer, the researchers and the users a very nice way to quickly find out, for example, given the sparsity, what accuracy degradation is, or the more interesting reverse problem. If you have an accuracy degradation budget, what is the best possible sparsity you can introduce to the model? And this question tends to be more challenging in practice. And next, I'm going to give it to Navin and to talk about the rest of network optimization and deployment.
Thank you, Elsie. Good evening, everyone. I'll be giving the second part of the talk on clustering or non-uniform quantization. So basically, I'll start with let's look at the top left figure here. So this gives an understanding of this difference between uniform quantization or non-uniform quantization or clustering. So uniform quantization means that you could distribute the quantization points uniformly across the entire quantization range, whereas non-uniform quantization means that you could distribute the quantization points as in proportion to the density of the weight distribution. So that way you could reduce the total quantization noise with the clustering or the non-uniform quantization. So the basic idea of clustering is that you cluster the entire weights of a particular layer into k clusters, and each weight in a particular cluster will be represented by the centroid of that cluster. So that way you need to only store the indices of the cluster, which will be far less than the actual 8 bits or even 32 bits. We use k-means as one of the traditional machine learning algorithm as a way to do the initialization for the clustering. So clustering enables weight compression, and this is not sufficient generally because when we do initial clustering, we will lose some accuracy, which can be recovered by doing some kind of retraining with the clustering constraints put into the network. So that is explained in the right side figure here. If you look at the top, the right side figure, that shows a 4x4 matrix of floating point weights, which are clustered into 4 clusters, which are represented by the different color codes here. That way, you only need 2 bits to represent each value in the 4x4 matrix. So during retraining, what we get is a 4x4 gradients for each 4x4 gradients, and we group them by the clusters, and then reduce them to get gradients for the centroids. And at the end, we update the fine-tuned, update the centroids based on the gradients of the centroids. So one thing to note here is that the third cluster centroid is 0. But after retraining, what happened is that went from 0 to non-zero, which would disturb the sparsity. So when sparsity reduces, the overall model compression reduces. So we have developed techniques to make sure that the sparsity is preserved when we do the clustering retraining. Uniform quantization. So what we get from a clustering is a clustered model where all the cluster centroids are still floating point, but generally the NPUs or neural processing units are generally designed for fixed point precision. So you have to quantize the clustered models to run them on the NPUs. So the basic idea of uniform quantization is to find the optimal quantization ranges such that we reduce the overall quantization error. So in the left example, you can see that if we pick the xmin and xmax, the quantization ranges to be the worst case data that is seen in the distribution, then you would have a lot of quantization noise because of limited resolution. Whereas in the right case, if you pick the quantization ranges to be very narrow, what you would end up is to you would have to saturate the weights which are outside the ranges to the x min and x max, and hence you would have a lot of saturation error, which is one form of quantization error. So the goal of quantization is to balance out the resolution and the saturation error. So we use signal to quantization noise ratio (SQNR) as a metric to choose the optimal quantization ranges. So here is the quantization workflow that we have developed. So first we start with the trained floating point model, and first we do quantization, weight quantization. So for each layer, we find the optimal quantization ranges, and then we evaluate and make sure that the model works fine with the floating point activations and quantized weights. And then collecting quantizing activations needs to be done very carefully because we need to collect the activation ranges using some form of histogram, and then once we have the statistics of the activations, we again find the optimal quantization ranges for all the activations one after another. So once we use something like about 100 calibration images to collect the activation statistics. So once we find the activation ranges, activation quantization ranges, we quantize the entire model and evaluate. If we have access to the training data set, we could optionally fine-tune the model to further improve the total accuracy. One key thing to make sure here, like in previous case, we have to make sure that the sparsity is preserved when we are doing clustering retraining. In this case, when we are doing quantization, we have to make sure that the sparsity is preserved as well as the number of clusters is also preserved, so that the total model compression, the model is still compressible. So quantizing nodes. The previous slide shows how we do the quantization. So here we talk about how which nodes to quantize, where to insert the quantization in the pipeline. So simple way to do is quantize each and every operator, which is shown in the first three examples. You could simply insert quantization around each convolution or fully connected or concat or residual, but that leads to loss in accuracy. If you quantize each and every operator, you lose a lot of accuracy. But if you have an option, you could choose to quantize after every fused layers. For example, in this case, you could choose to fuse convolution and bias head, or convolution, bias head, batch norm, and value. And you can fuse them, and that improves the overall accuracy of the quantized model. Equalization is a technique that we use to make the models easier to quantize when we don't have training data set to do the fine tuning after quantization. So, the one thing that we observe in models is that the min and max ranges across different feature maps in a particular layer varies a lot. So equalization, the goal of equalization is to make sure that the min and max of each feature map in a layer roughly equal, so that we use the full quantization range. So how this is done? So first we scale the current layer weights to make sure that the ranges, each feature map range is fully utilized, and then that would lead accuracy drop in accuracy. So you should compensate for whatever change that you have done in particular layer by doing exact unscaling in the downstream layers. So that is shown in this the bottom figure. The left figure shows different layers of mobile net V2. So the y-axis there is the min and max of per channel, and each box is a different layers in mobile net V2. And x-axis is the channels in a particular layer. So before equalization, we can see that the min and max of each channel vary a lot, almost like an order of magnitude. But after equalization, you can see that either min or max or reaching the total the max of that layer. So the goal is to see that the entire range is fully covered in the right side figure. So what does this mean to accuracy? So the rightmost figure shows that. So we can see that quantized 8-bit accuracy, there is about 2% improvement when we do equalization. Whereas if we do further quantization, like 7-bit or deeper quantization, 7-bit or 6-bit, we would see more than like 10% or 20% improvement in accuracy if we do equalization. All this is without any fine tuning. So collaborative optimizations. I've previously mentioned that when we do quantization, we make sure that the sparsity and the clustering are preserved. This figure is just to illustrate how the data distribution, weight distribution looks like. So the top left figure shows an example of original weight distribution ranging from -3 to +3 as an example. So once we start doing pruning, in this example, 50% sparsity. So what we do here is any above 50% of the weights close to zero will be snapped to zero and do fine tuning to improve the accuracy. So this is roughly how the distribution would look like. So we have a huge spike at zero, and the weights will be apart at a small threshold apart, in this case 0.276 away from zero. So once we do spark pruning, we go to the clustering. In this example, we are clustering to 16 clusters. So here we further make sure that the sparsity is still preserved at 50%, and what we get is 16 unique floating point values as the cluster centroids. And again, fine tuning to make sure accuracy is not as fallen off a cliff. And next point is to quantize the clustered model while making sure that the sparsity is preserved at 50%, and clustering is there are 16 unique cluster points. You can see that the final output of the quantized model has 50% sparsity, and it has 16 unique unsigned intake values, quantized weights. LC has mentioned about different hyperparameter choices, for example, heuristic or uniform distribution or reinforcement-based techniques. So we have developed other techniques such as sensitivity-based hyperparameter tuning. So we know that neural networks work very well even in 8 bits, but it's not that all layers need 8 bits. There are some layers which could go down all the way down to 2 bits or 3 bits. So here is how an example where MobileNet V2 we have gone down to 3 bits or 5 bits in some layers. So the goal is to sweep the quantization bit width from class like 8-bit down to 2 bits and find a point where your accuracy does not drop a lot. And with that bit width frozen for that particular layer, you go down to the next layer and then start doing the quantization sweeps to get the next the best quantization layer, quantization bit width. So this makes sure that the quantization error is cascaded from one layer to the other. So in this example, we started from this largest layer so that the entire the model size is reduced a lot. So in this example, in the MobileNet V2, what we get is an effective bit width of 4.5 bits with only 2% loss in accuracy without reaching. But once we start doing fine tuning, 1.5% accuracy is recovered, leaving only 0.5% drop in accuracy with an effective bit width of 4.5 instead of originally it used to be 8 bits. So model optimization such as pruning, clustering, quantization, and algorithm optimization such as Vinograd are key for hardware and algorithm exploration and hardware validation. So size of optimization space, it's a huge optimization space. For example, if you look at if you have a network with 100 layers, you have 100 times the number of combinations of the pruning, and it grows exponentially large in terms of optimization space. So learning rate and the learning rate schedule and the kind of optimizer that we use for doing fine tuning further expands the hyperparameter search space. So duration of trials, so it might it is a sum of the different uh, optimization trials for pruning and clustering and quantization and so on. Collaborative model optimizations are really key to do an end-to-end technology exploration. So sparsity preserving clustering is one such collaborative optimization, and sparsity and clustering preserving quantization is another collaborative optimization. So to reiterate, so on-device ML solutions has three components. So model optimization is one of the key components, and followed by optimized software and optimized hardware. Thank you. We are open for any questions.
So we will move the Q&A session towards the end. Now, the second talk is about Synthesis, a software library developed by ARM that provides optimization on ARM microcontrollers. Our speaker today is Felix, who actually flew all the way from snowy Sweden and joined us here. Welcome.
Hello everyone, thanks for joining today. I'm Felix, and I belong to the ARM's machine learning engineering team based in Sweden, and I'm also the maintainer for the CMSysNN library. And today I'll be talking through what CMSysNN is, and like how we go, how our workflow is, and yeah. So let's get started. So the CMSys or Cortex microcontroller software interface standard. It is a collection of API definitions, utilities, and so basically it's targeted to accelerate your microcontroller development. And it is supplied with the Apache 2.0 license so that you can use in open source or any commercial projects as well. And it is open source on GitHub. And this diagram is just to show that CMSys has way more things in it than just CMSysNN. And CMSysNN is actually the newest kid in the block, you could say. And one thing to mention here is that it says Cortex A5, A7, and A9 as well, but we don't have that for CMSysNN. I can see a lot of cameras on this picture, so I'll just wait. Yeah. So, why target Cortex-M on Cortex-M CPUs? The obvious answer here is to accelerate machine learning on edge devices. And now we have more than 47 billion shipped units of those, so that makes it quite logical. But then, like you could say, we did have billions of units a couple of years back as well. So what has changed now? And that would be the availability of models, or availability of networks with low memory footprint and max for computations in it. So for example, if you take a MobileNet V2, it has around 3 megabytes of parameters and 307 million max in it. Now, if you take a person detect model from TensorFlow Lite, which I believe is based on MobileNet, it uses just 250 kilobytes and just 7 million max. So now this, I believe, has played a big role in why we're talking about the possibility of running a neural network models on Cortex-M CPUs. Now, if you take ARM Cortex CPUs, you have around 9 different CPUs that you can choose from. Now, so what is the relevant question that you should ask when you're picking one for your application? So, given the choice that you have, so at least the first question that I would ask is it SIMD capable, or can it handle single instruction multiple data? So, if if your network or if your model has around, if you're speaking about like 10 million max, then it is quite a relevant question. Then it's quite obvious on like which side of this you would take. But then today morning, like we had Jim Davis, like who showed a network which used a Cortex M0, right? So there again, like it depends on what kind of inference speed you're looking at and what's the complexity of your network. But this is a good point. This is a good question to start, I believe. So, and now a couple of slides about like how we go about with optimizations, and like so basically to give you a window into like how we work. So, what do we optimize first? We take the big three first. That is convolution, depth-first convolution, and fully connected. So we take this and we optimize them for SIMD and non-SIMD instructions. So we begin with this, and then we go into specializations of it, like a point convolution, and then we go for pooling and softmax, and then we go to the other operators. So what is next in pipe for us? Right now we are focused mainly on adding kernel support for ARM's Helium technology, which, as you believe, which you know as the new vector extension support for Cortex M CPUs. And I can say that it is an absolute delight to program using the M-profile vector extension. And if you haven't tried, I would recommend you to. All right. And so, if you take an optimized kernel, like I look at an optimized kernel and I see two aspects to it, or two components to it. The first one is the optimization technique. And this could be some kind of memory reorganization, like as a lot of you are aware of image to column technique. And something like that, that is the first thing that we try. That is something on theory or in paper. And then we go about with optimizations using intrinsics. Now, yes, so again, like, so we basically use SIMD instructions. So we basically use intrinsics to nudge the compiler to use the SIMD instructions. And and one important aspect of this is like what it provides you is that despite different optimization levels that you could use in your application, you would get similar performance results. So if, let's say if you have an application which is constrained for space, and another application might be constrained for cycles. So even though you use different optimization options for your application, you would actually get similar performance results, and that is the consequence of using intrinsics. Right. And now a little bit of what we have been up to the last few months. So we've been working closely with the TensorFlow Lite micro team in integrating SIMD with TFL micro. And this one is like basically, this is just to add support for integer rate quantization. So as a lot of you are aware, like TFL micro supports uint8 and int8 as well. But what we do right now, it is intended only for int8. So if you take the simple picture on the right, so you have your application, and then you have your TFL micro runtime. And then what you do is like you plug in seamless and then optimized kernels into it. And so during the build system, like you would check if there is an optimized implementation for the operator, then the TFL runtime would pick it up from seamless NN. If it doesn't exist, then it will fall back on the reference kernel implementation. So what this gives you is like you'll never be stuck for a non-availability of an optimized operation. So you'll always be able to build your application and run through it. So now there are many ways that you can use TFL micro and run your application. And using an ARM embed enabled board is one of the many options that you have. Now, the thing is, like, if you don't want to faff around with make files or scatter files, then this is a very good option to do, because you really don't need to know much before you can get your application running on a board. So, like the figure on the right, it's basically like what I've done there is like I've just sorted out the boards which are available, which are embed enabled, and which have Cortex M7 or an M4 CPU unit. And you have 82 different boards to pick from that. So this is just for Cortex M4 and M7, which have the DSP extension. Okay. And this is the steps which are involved in using Embed OS or an Embed enabled board in TFL Micro to get up and running. So the first thing is like you clone TensorFlow from GitHub, and then you generate a project with or without the optimized kernels. So the way TensorFlow build system works is like when you create a project, like it copies all the files necessary that you want into a separate project, and then after that you write your application or your main file, and then you just compile on Flash. So the process to generate a project looks like that. And the way that you include your optimized kernels is basically you just say tags equal to same sys in it. So, and then you do that, and the optimized kernels will be automatically included for you if it is available. And when it comes to compile and Flash, this is using Embed OS. And the thing is, like, you don't really need to know what underlying board you're having and like what processor you're using. You just say, give an auto option, and the Embed OS automatically detects what board it is, and then it does the rest of the job for you. And right now, you have to specify those two macros as well. But we're trying to get rid of that so that the only change that you would have to do to use optimized kernels is just to specify the tags as same as in it. It's not in, but it will soon be. So this is for the step 2 generating a project. This is a slightly elaborate view of what it means. So TensorFlow Lite Micro first begins with all the operators that it has. And then it goes through each operators one by one. And it sees if there is an optimized kernel available for it. If it has, what it does is like it picks the optimized kernel and puts it into the basket to be compiled. If it doesn't find an optimized kernel, it goes to the fallback solution. So that is right. So now when we come to running on edge devices, we're always interested in the speed up. Like, what is the speed up? What speed up do I get? That is the number that is interesting. And I would say that like we have to be really careful in interpreting those numbers. And so for this presentation, like what I did was like I took an int8 model from TensorFlow Lite Micro, which is not in yet, and of the personal detect model, and ran it through a ST nuclear board using a Cortex M7 processor. So if I have to sensationalize the result, I can say that it gives a 17x performance when compared to TensorFlow Lite Micro's reference implementation. Though it is a very factually right statement, it is also irrelevant and a pointless statement because that isn't how it is intended to be used. So this is the complete picture of it. So you see, like there is in Embed OS, like you have something called as profiles. So a release profile is the relevant profile to use because that is the mode that you would use on a final project. So, and then like I just changed the optimization levels of that. So OS optimized for space, and then optimized for speed, and then OG, and then O2. So you can see that the speed up, the relevant speed up that makes sense is 2 to 7x. That is the speed up that you can actually get from using optimized curves. And also, like, if you can see that, despite the different optimization levels, the cycles taken by the seamless and an optimized version is in the same ballpark. 30% is not exactly in the same ballpark, but relatively speaking, here it is in the same ballpark, you could say. So that is one of the that's the other advantage that you get from using the optimizations using single instructions. So, all right, and here I have put some useful links on on the resources that we've used in the presentation. And like today, like talking to people around, I had mixed reviews about CSS and like their experience in using it with TFL micro. And it is a work in progress. And so if you have any good experience, I'm happy to listen. But at the same time, like, I'm more interested in cases where it hasn't worked for you. So please talk to me on like what was it that didn't work for you, and I'm happy to resolve that. And I don't think I have a demo, but yeah, but maybe I'll just show you one screen grab on how a project looks like. So the left-hand side is a list of operators. Like this is a screen grab of the project that was created when using just TensorFlow reference kernels. So you can see that I've marked out a couple of operators like convolution, depthwise, and fully connected. On the right-hand side, you have the option, like you have a project when it was built with CSS optimization. So you can see that what has happened is like those 3 files, they disappear, and they're replaced by the optimized version, which goes into the CSS folder. Okay, that is basically what I have, and I think 7:30 is the right time. Thank you very much.
So our third speaker will be Kwabena from OpenMV, who is the president of OpenMV, also an MCU guru. So while he set up his laptop at the back, probably we can take 1 or 2 questions for the first 2 talks.
This question is for Felix. I'm curious why the emphasis on 2D convolutions, given the role of 1D convolutions, often in the form of depthwise separable convolutions in modern network structures. Shouldn't you be optimizing for the 1D convolutions?
1D convolution as in point convolutions?
Or depthwise separable.
Separable convolutions.
So n by 1, not n by n.
All right. So that would be, I mean, what we're trying to do right now is like we basically we want to integrate with TFL micro. And we're starting with this, but it's not enough.
Any other questions for our speakers? They must have done an excellent job. Okay.
Oh, that's fine.
So can you explain a little more the comparison, the optimization that you showed, like the time 16, 17x and 2x, 8x? What was the comparison? So you compared with what? So 8x versus what?
All right. So the numbers that you see under the column reference kernels, that is using TensorFlow Lite Micro's POC implementation without C2SNN. And then C2SNN optimized, those are basically optimizations using intrinsics and other techniques. It's comparison of those two.
A quick optimization question on that one too. What was the frame rate roughly with the 17x for like overall performance?
Yeah, the thing is, like, I don't want to get into frame rates, which is why like I put in the cycles. So it depends on your speed, on the CPU speed that you choose.
My question is for, I think, LC, the first speaker. You described a really impressive array of optimizations that you can apply to fixed point. Are these optimizations something that you have developed entirely with in-house in your team? Or is it part of a tool that can become available to ARM users?
That's a thank for the question. And just to be clear, we are from the ARM machine learning technology group, so we do investigation of technologies, and but you know, it's definitely clear that we're not doing this for fun. So I think the best way to get feedback on that kind of question will be talking to the marketing side of ARM. Sorry. But yeah, if you have more questions, we can also take it offline.
Okay, hey everybody. Let's just keep the slides. All right, great. We're on live. Okay, so I'm going to be presenting TensorFlow Lite for microcontrollers on the OpenMV H7. So far you've heard about tinyML and how it can offer really nice performance. But did you know it's actually available on hardware today? So it's not like one of those things where it's like going to be released in the future. We have it available on every OpenMV right now. So that's what I'm going to be talking about. So first, you may have heard the OpenMV being talked about by Chris. Basically what we did is, this is a hobbyist project that's been running for about 5 years. And we more or less took a tour of computer vision and just started porting algorithms to a microcontroller. The whole idea was, can we get high-level computer vision algorithms away from requiring Linux and lots of memory and really embed them into a low-cost CPU such that they can be executed on the edge. And the whole purpose of this was really to make computer vision easier for folks who are just starting with it. But we're starting to see a lot of commercial applications being interested in this kind of thing, where we have computer vision on a really cheap piece of hardware that doesn't require any external DRAM, just a camera and a processor and strapped together and running at blazing speed. So the OpenMV is this little guy right here. It's a ARM Cortex M7 microcontroller with a camera. That's the two components. Doesn't have anything else. And it's an open source hardware and software product. So we have a complete release of the schematics. You can build it into your device. You can remix it, whatever, we don't care. It's also an open software product. All the firmware is available, and additionally the IDE is available. The system runs C code. So internally, we have a large amount of C firmware that we pulled together that actually does all the work. But we present a Python interface to everybody who uses our system, such that it's easier to program. And so we use MicroPython to be the operating system effectively. MicroPython is an OS though, it's single threaded, no context switching or anything, just bare metal, runs in the loop. It has interrupts if you want to do anything else. But the big idea is we provide a Python interface such that you don't have to worry about making the system. Python makes it super easy to reprogram repeatedly. So if you want to start and stop the script, it's not like minutes to figure out a change in your firmware. Anyway, so the processor on board is a ARM Cortex-M7, the STM32H7. This slide is a little bit out of date. And I think it's because this is actually a picture that I copied from a previous slide to do less work for this presentation. It's a 480 megahertz processor now, so the CoreMark score is actually faster than a Raspberry Pi 2 single-threaded core. So you are outperforming pretty much an ARM Cortex, ARM A9 processor in single-threaded performance. It doesn't have SIMD vector instructions, but in terms of single-threaded performance, it outperforms the A9. Additionally, you have 1 megabyte of RAM and 2 megabytes of flash. So the genesis of this thing is there was a project started at Carnegie Mellon University called the CMU-CAM back in 2002. And the CMU-CAM was basically strap a microcontroller, an SX48 at the time, to a camera and see how you can make like cheap computer vision. And back in 2002, this was the only product in the market that existed in terms of being like computer vision in a microcontroller. Everything else was desktop PC. And so that morphed a few times into multiple cameras. Back at Carnegie Mellon, I was the guy who did the CMU-CAM 4, and then there was the CMU-CAM 5, and then from that idea, I started the OpenMV-CAM, which was to build a company around making this thing available and keeping it in stock. Because the CMU-CAM is basically a contracted design of Carnegie Mellon, and wasn't really set up as a company to kind of keep that product on the market indefinitely. Anyway. And so one of the big ideas behind this platform is that you have computer vision and I/O control in the same package with the same program, like one script controlling everything, such that you're not going between multiple systems and having to share data between multiple processors in order to sense, plan, and act. Anyway, so what makes our product really successful, I guess, is we provide a OpenMV IDE, which is a piece of desktop software for Mac, Linux, and Windows, and even Raspberry Pi, where you can write Python code in one window, you can see the frame buffer in another, and you can see serial terminal output and some eye candy for histogram data. It's open source also, so if you wanted to remix it or rip us off or whatever, you can do that, and add whatever new functionality you want. The big thing, though, is it makes it easy to interface with our system. We try to prevent you from, we don't want to like drop you into, good luck, here's a bunch of bare metal tools, have fun. We kind of make it a managed experience, and then if you want to go deeper, you can, but you don't have to. And so what the OpenMV-CAM is used for, I think if I play this slide, it starts showing the demos, let me see. Okay, there we go. Yeah, so the OpenMV-CAM is used for all kinds of things. Right now, we're just like a hobbyist toy, and that's where we've been, but I'm kind of want to move the company towards high volume manufacturing. So our big sale point right now is color tracking. That's what people like to do. That's what that's what the original CMU-CAM was about. Color tracking is a very easy filter. Just threshold all the pixels in the image between a color min and max, and you follow it. And using that, you can track colored balls. You can make line following robots, all kinds of great stuff. Okay, cool. All right, so we're going to talk about TensorFlow Lite for microcontrollers. Okay, and we're going to do a demo on person detection. Okay, cool. So, how easy is it to do person detection on a OpenMV-CAM? All right, so let's show that off. Let's just close all these examples. Okay, so this is OpenMV IDE. It's got a bunch of stuff from the previous output because I've been demoing this all day. All right, so here's the OpenMV-CAM. We're just going to plug this in to the PC. And once we do that, the OpenMV-CAM is going to get enumerated as a USB device. It's going to appear as a flash drive. And so this is the OpenMV-CAM H7 Plus. This is a new model we're about to release. It has 32 megabytes of ST-RAM on board with a Cortex, with an STM32H7 processor. And it also has a quad SPI flash memory. And so the quad SPI flash is memory mapped as a OpenMV disk in the system. So when you plug it into your PC, it appears as a 16 megabyte flash drive on the computer. And you can literally just drag files from the PC to the OpenMV-CAM, and they'll be stored on that flash drive. And so, for example, in this example, we have MobileNet and MobileNet labels just all sitting on the flash drive along with some other stuff. Anyway, we're not going to run MobileNet because it's not really that interesting, since it's more of like a canned example to show performance. Instead, we're going to run a person detection network. All right. So basically, in the firmware image, we've embedded Google's TensorFlow library. So we have TensorFlow running on board. Google just released this recently for all microcontrollers. It finally got to a point where it's actually usable, though. It was released back in March, but kind of broken, and it's still working its way to not being broken. But it's good enough right now to show off person detection. And so in this example, I'm going to show off it being able to detect people in the field of view. So I'm just going to change this example real quick to being in color, and we're going to run it. Okay. And so first we connect to the OpenMV cam, and we can see a little terminal output here. And you're going to see in the podium is a little bit movable. You're going to see in the top right corner it detecting a person or no person. All right. Can I get someone to walk up to the front in the stage? So right now it says no person. Let me actually make that text red real quick. Hold on. Yeah, so the camera is the one that actually compiled that code and ran it. Okay, so it's saying no person. You can kind of see the red in the top. Okay, so we put this in the field of view, a person. Hold on. Okay. Oh, wow, the picture quality is bad. Demo fail. Give me a sec, actually.
Get in the light.
I'm just going to change the camera sensor all out real quick. So we have a multiple camera modules this guy can run. And so that was showing off a new camera module that we haven't quite fixed the driver for yet. So we're just not going to use that one. Okay, so this is one that we have driver fixes for. Okay, cool. So the camera appeared, enumerated. Okay. Connect. All right. And it's still, okay, wow, it's pretty washed out. Okay, so you can see it detects me as a person. And then if I point it at not a person, it detects no person. Amazing. So this is showing off person or no person detection based on TensorFlow Lite. So Google just released this running on a running on an Dec microprocessor. And so that's a pretty cool demo, but the Dec micro doesn't really go at super high performance. It's meant for audio detection. And so we have a much more performant processor that can hit about 2 FPS in real time, showing off person or no person detection. And so once ARM CMIS is finally released and integrated into Google TensorFlow without any bugs, we should be able to get this running at about 10 FPS on OpenMVCam H7. This also runs on the OpenMVCam M7. And so in total, we've sold about 20,000 units of all these cameras in the wild. And we have a lot of users equally with all those cameras. And so this is software that is available today to many different people on a lot of hardware platforms that you can buy. And basically get started with TensorFlow on a microcontroller. Cool. Now let's see, does it find anybody else? No, it's super washed out. I'm not sure why. Let's see, is it actually auto-game too much? No, not really. Okay, don't want to solve that problem right now in a live demo. Anyway, so far it works for me. You want to get up here and see if it works to find another person? Okay, come on, jump on the stage, man. Okay, is he a person? Come on. Oh, it says he's a person. Okay, great. Awesome. Awesome. Does it detect it detects no person when he's not in the field of view. Great. And so this is a TensorFlow model executing on this camera. And you can imagine, just with that simple application of person or no person, you can easily make a sensor that can detect when you enter the field of view, turn on a light, turn on some kind of system, open a door, whatever. That's just a simple kind of baby example. And then if you actually have your own data set, your own application, you can deploy this kind of camera technology to detect whatever you feel like. And so I'll show a more advanced example. This isn't really as compelling, but hey, So you can actually run MobileNet on this thing. And so MobileNet is a really large network, usually like a benchmark for a lot of different stuff. And so with the OpenMVCam H7 Plus, we have SDRAM on board. This allows us to actually fit the MobileNet model along with the activation outputs. And so we're just going to run this on the system and see if we can detect here. So look at the serial terminal on the bottom. It's not going to really print anything on the top right corner. And so if you see right down the bottom, it's going to tell you the top 5 detections. And so the top 5 detections, it's a paper towel, a seat belt, cash machine. Let's see if you got to hold it steady and not have like moving. Okay, I think it's a monitor, desk, planetarium, screen, laptop computer, notebook computer, computer keypad, monitor, keypad, notepad, planetarium. And so that is Google's MobileNet running on board the system. It's only getting about 0.2 FPS. Obviously, because we're not like an application level processor, it's not going to be like impressive performance. But still, the fact remains we are running MobileNet with all of 1,000 class outputs on this embedded system. And then we are choosing the maximum class output of 1,000 class outputs and outputting that to the screen. And so the person detector network shows off more of a realistic application where you tune the output of Google MobileNet to something useful with just detecting between 1 or 2 classes and actually having it running on board. And so again, once CMSNN comes out, you're going to get about a 5x performance boost once that is available. Right now, Google's code is extremely unoptimized and doesn't do any loop unrolling or use any of the SendD instructions that were previously talked about. So you're getting the bare minimum performance of the processor currently, and it'll go up from here. So this feature is available on all OpenMVCams right now. It's still kind of alpha because Google's TensorFlow library is still somewhat highly broken. So it does run the person detector, it does run Google MobileNet. That's because it only supports really convolution 2D and convolution and depthwise convolution. If you try to use a lot of the other operators, you're going to run into weird issues that are kind of intractable to solve until Google fixes all their code. So in terms of what that looks like, so on the OpenMVCam, we have a documentation that we just released, and so our latest firmware supports TensorFlow. And we have a TensorFlow model. So you program the OpenMVCam, by the way, in Python. And so in this code, the way that worked was for MobileNet. MobileNet is a model, and we just build a string for the name of the model on the SD card. So there's a lot of different Google MobileNet models you can run, for example, as you can see here. Each one is as you make them bigger, they perform better, but they take more time to run. So if you make it really tiny and it'll have bad performance, you can get like 1 FPS, but the cost is the accuracy is terrible. Anyway, so the way you kind of work this system is for the OpenMVCam, we just call the snapshot function. That takes a picture, it loads into whatever our frame buffer is. And then after that, you can just call tf.classify. And you pass it the string name of the MobileNet file on disk, along with an image object. And then we literally take care of loading that model into RAM temporarily on a stack. And then we also take that image, reformat that image into a way that it can be fed into the model, execute the model for you, and then take the results and then put that into a Python list of ints or floats, and then return that float. And we do all that for you behind the background. So literally the code you were running to do this was the pre-canned example of just clicking the open file button. So pretty much no work on your part to get basic MobileNet or any type of neural network running. We also support a sliding window methodology. So if you feel like wasting all of your processor time per frame, you can specify a scale ratio and have the thing actually slide the detector window over the image and rescale it via a scale number as it slides the detector window in order to detect everything possibly at different scales and at different positions. That though, of course, you need to pick a network that's not super heavyweight like MobileNet for that to actually be anywhere near real time. But we kind of give you that feature set on board. Anyway, so back to the API for this. So we have a TensorFlow model. This is going to support two functions mainly. We support classification, So that's where you can execute the TensorFlow model and then output a series of class labels. And so we kind of wrap up all the TensorFlow happiness that you'd have to deal with and make it super easy for you. Just thinking about passing it a path to your model and the image, and then outputting a list of floats that represent your model output. And then you just match those to a, typically just match those to a list of class labels like so. Then we also have a segment function. So the segment function will take a TensorFlow network, process it, and then output a list of image objects, which are 2D images representing the different class segment outputs of a segment to a model. We'll plan to add more model variations in the future as Google releases more support. Right now, classification and segmentation are about the two things that seem obvious to do with it. Anything else like bounding box detection is going to require more engineering effort from Google to kind of enable that downstream for us. But we kind of see that as not necessarily being a technical limitation, just given their time and fixing other bugs, that will be a feature in the future. And so on OpenMPCam at least, we support 2 ways of executing models. You can either load the model in RAM and then execute it repeatedly, or you can load the model each time per loop repeatedly into RAM off an SD card and execute it and then throw it away. The difference is if you keep the model in RAM, it uses up a huge amount of heap space. And so that's kind of tricky to use versus repeatedly pulling it off an SD card per execution. So one gives you more performance, but uses up memory. One gives you less performance, but is easier to do. Finally, we only support a set. So Google basically has this thing called a all ops TensorFlow file. So Google will list out. Let me just make that bigger. Let's get some. Ooh, okay, cool. So Google TensorFlow is a library that supports a series of convolution operations and other various things. And we support pretty much as many possible operations as Google supports. And then some of these operations are optimized using ARM CMSNN. So things like the fully connected operation, max pool, depthwise convolution 2D, those are all ARM CMSNN optimized operations. And so those will run faster than normal because someone is taking time to loop unroll things and to figure out how to use the SIMD instructions. All the rest of them are just like very generic C code that no one spent any time thinking about how to make that faster. It does the correct thing, but might be slow. And so we support these operations, and this kind of evolves over time. So right now, Google has kind of support for depthwise convolution, fully connected, and convolution 2D really, and concatenation, where they actually explicitly implement the version number. So if you take our product now and try to use it, one thing to keep in mind is if you use Keras to compile your code, you may run into operation version problems because Google hasn't explicitly defined which operations they actually support yet. This thing is a really day-to-day kind of thing though, so literally some stuff was broken 3 days ago and then Google fixed it, and then we updated our firmware and then it was fixed again. And some other stuff is broken. So we kind of foresee within a month or so that Google's going to have all these issues worked out. And the ability for you to kind of run any network, more or less, it will be available on a microcontroller. All right, that is all. Thank you.
Any